4.3, what was the answer for that?
Who is this asking?
Jordan.
Jordan, did you email me about it?
Email you? No, I just saw the grade yesterday and
Yeah.
I got
If you have a specific question, please email me about it. All right. I want to, and I'll respond to you. I want to advance with with the topic that we're on. Okay, just email the question, and then I can I will either reply to you directly or I will address it in the next lecture. If that's all right.
Okay.
I mean, I did go over all of the quiz, right? I did go.
I'm talking about the midterm.
Oh, the midterm. Okay, yeah. Please email me and I'll answer. Thank you. Okay, excellent. Any other questions before I start?
About the midterm?
Yeah.
I put in a regrade request. Will you be looking at those, or should I just email you?
No, I will look at them. Yes, I received a couple of those. I will look at them. Yeah. Okay. Very good. But yes, it sounds like the new email went out yesterday, and it looks like now you can actually see your grades. Again, though the grade is out of 110, the credit that you get for submitting homeworks and quizzes actually just adds, right, to your final grade. So in fact, the actual numeric grade that you see is probably actually a very good indicator of like your standing in the class right now. So let's say that if you got, I don't know, 95 on the midterm, then your standing is you're somewhere between A- and A. Okay, very good.
Professor, can I ask you a quick question about the homework last night? Quick question. Everyone says quick question. Just
yeah. Yes, you can. Just let me say one thing. So the homework was posted, yeah, but I said technically I didn't assign it yesterday, so technically it's not due today. Technically it will be due tomorrow. But yes, it has been posted. So what's the question?
That's thank you.
Oh, that was the question. Yeah, it's not due today, but you know, you could have started working on it, or you can start today. And you know, just so that it's not mysterious. This is the homework, the first part of it, which is just sort of like more practice exercises that we've done so already. And then the second part is this one also, practice exercise. So the homework is not on anything new, then we will have additional homework on the new stuff. Coming up.
Did we have to minimize that one using a K-map, or we can do anything like using the laws that?
So with these practice assignments, you can use any method you would like.
Okay.
Okay.
But it seems like map method. You know, we want to minimize. We still need to eyeball it. It's non-deterministic, or I guess it's deterministic, but you kind of have to. There aren't really great steps to go through to do this, or.
Well, no. So right now we didn't finish going through the steps with the tabulation method with the prime implicant table. So we're going to I'm going to get back to that right now. I think though using either that or the K-map, you can find the minimal form with great confidence. It's maybe not as a hard of an algorithm as maybe you would like to have, but with a little bit of practice, you can be very confident that you found the minimal form. And there was another question. I heard a female voice.
Yeah, you mentioned that like our midterm is a good indication to where we're standing in the class. What if we like failed the midterm? Is there like going to be any extra credit assignments or like sort of like a makeup or like anything we could do to raise our grade?
Well, so your homeworks and quiz submissions, they raise your grade, right? So if you didn't do well on the midterm, but you've been submitting everything and you do well on the final, you will certainly pass. But also, so I have a lecture right after this, but let's see if I can end a few minutes early, and I will have little office hours, and maybe you and I can speak in the office hours privately.
Okay, thank you, Professor.
Yeah, absolutely.
Do people in the class, sorry, do people in the class want to get a study session going, or a a Discord something, or I don't know what the kids do these days, but we're kind of
Yes, we do.
on our own. How do we manage that? Professor, maybe is that something you could coordinate, so because we can't really coordinate it, or can we do that now and talk ourselves?
I think it's a great idea. I think it's a wonderful idea. I know about Discord, but I haven't really used it myself. So you seem to know about it. Is this Guy, or who is this?
Yes, this is Guy, but I have no idea how that works.
So what would it entail? What would I need to do?
I don't know. Does anyone know how to set up a Discord channel or whatever?
If you enable the chat messages for us, we could send a link, share a link that everyone will be able to join.
Totally.
So who is going to create it, though?
I say the person that suggested it.
I'll figure it out. And
I'm sorry. So look, how about this? So who knows
I'll figure it
how
out,
to make...
and I'll put a link in the chat tomorrow.
Let's do this, Guy. This is, I guess, your assignment. Set up a Discord server if you can, and then email me the link, and I will post it on the course page. That should work, right?
Will do.
Okay, but I have to tell everyone that you have to be extremely respectful on this Discord server, because in the past there have been cases where people have behaved themselves very badly on the Discord server, and we cannot tolerate that, right? So you have to be on your best behavior. And actually, now that I think of it, by default, as far as I know, these Discord servers are anonymous. And I think the only way that I could allow this in good conscience is if the server was set up in a way that the membership is not anonymous. So Guy, or anyone who knows how to do that, if you could email me. So what we need to do is we need to set up this Discord server so that it is not anonymous, so that if somebody misbehaves, we know who that is. Does that make sense?
Yeah, sure. If I'm setting it up, they'll have a zero.
Okay, because we don't want this to be like, a situation with Twitter trolls and okay, but yes, with all these caveats, it's a wonderful idea. So we'll try to make it work. So let's go back into the lecture, and we'll continue with the prime implicant table. Do you see it as full screen, or do you see it as part of the window?
Full screen.
Full screen. Okay. Oh, I see. Okay, I don't. Just one more second.
Or maybe it's part of the window. I see two black columns.
Okay, let me redo it. Let me redo it. Sorry, it's I'm doing it wrong. Yeah, I need to share it differently. Share application screen. Do entire screen. Share. Okay, now it should be truly full screen, no black bars. So just to bring us back where we were, right? We first use the tabulation method to find out all of the prime implicants. And now, knowing the prime implicants A through I, we want to somehow algorithmically come up with the minimal form, right? Find the essential implicants and then the combinations of the non-essential ones that will in the end produce the shortest possible form. We know how to do this with K-maps well, and now we're going to do this with the prime implicant table. So we started that yesterday, but I want to go over that bit one more time so that everybody is caught up. Right, so we had a very long, tabulation table, right? That where we were able to come up with the prime implicants. If it's hazy, please review those slides. Now, once we have all of the prime implicants, right, we make another little table. This one is smaller. It's called prime implicant table. And this table is for each implicant, we have a row, right, from A through I. And for each min term, for each one on the imaginary K-map, we have a column, right? We don't have any columns for don't cares because we literally don't care about them, right? But we do need them for ones. So 1, 2, 3, 4, 7, 8, 12, and 15, okay? And then we mark with little crosses or X's where we mark essentially which of the min terms are implied or covered by an implicant, right? So for example, someone's mic was on, please turn it off. So for example, A covers 8 and 12, right? Here it looks that it also covers 10 and 14, but 10 and 14 are the Ds. We don't care about those, so we don't put them on the board. And then let's see, for example, I don't know, G covers 1, 2, and 3. So let's look G, 1, 2, 3. Here we have 0, 0 is a don't care, right? So this is what the prime implicant table represents. So now we're going to iteratively repeat a sequence of 3 steps to continuously simplify it. Yeah, so the 3 steps are: 1, find essentials, put them in the minimal form, and eliminate them from the table. Right? Then the second step would be, once you did that, once you eliminated the essentials from the table, then you remove dominated rows, then you remove dominating columns, and then you repeat, right? Until you cannot repeat anymore until a minimized form is obtained, right? And here is the note that when one has only one X in its column, then the implicant corresponding to that X is essential, right? So this is the test for the first step. Let's read it again. When one, by one we mean these mean terms, yeah? If any of these ones has only one X in its column, then the implicant corresponding to that X is essential. Can somebody explain that in other words? Like, why? Is it just like a magic trick, or what is the meaning behind that? Why a single X in a column makes the implicant that intersecting with that column at that X essential? We don't seem to have such condition at the moment, but we will hopefully soon.
it indicates that only one implicant covers that term, and no other implicant also covers that term, so it has to be essentially.
That's exactly right. Is this nephew?
Jordan.
Jordan, okay. Yeah, right. So let's say that, imagine that we didn't have an x here. Let's say that in column 7, x was only here. That would mean that the 7, or the min term number 7, that square, is only covered by a single implicant I, which necessarily makes that implicant essential. But as it is, every column has at least 2 x's, so we don't have any essential implicants, so we cannot cross them out, right? So we go to the second step, dominated rows, right? So what we have here is, for example, row, well, before we do row I, we have a couple of such conditions. We have row C dominates row A, right? Meaning that implicant C covers all of the same ones as implicant A covers, and more, right? That means that we don't need implicant A, right? This dominated implicant is redundant. We don't need A to cover 8 and 12 because C covers 8 and 12 and also 4. Yeah. If we did not have don't cares, that would also mean that A is entirely within C, that C entirely overlaps it. But because we do have don't cares, it may not mean that. It may mean that they substantially intersect. But that difference or distinction is without difference in our case, because all we care about is to cover all of the ones, right? And the ones that A covers, the 8 and the 12, C also covers, and it also covers 4, so we can just get rid of A. Right, so C implies A, or contains A, and we get rid of it. Okay. And then we have another conditions that is like that is such where I dominates H, and we don't need H, and we'll cross it out. And then we move on to the third step, dominating columns. Right? So with the rows, we remove the dominated ones, and with columns, it's the other way around. Now let's think about why. So first, let's find some dominating columns. So it looks like 1 dominates 3, right? Now, can somebody explain to me in sort of more English conceptual terms, what does that mean for column 1 to dominate column 3? Okay, well, so literally what column 1 means is that that one little square, is covered by 1, 2, 3, 4 implicants, B, E, F, and G. Right? But it doesn't need to be covered by 4 implicants, right? It's enough for it to be covered by just 1, right? And column 3, right, it's a different one that is covered by only B and G, right? Both of those also cover 1, right? So we don't need the other ones. We don't need the E and F, right? We're removing them because they're effectively not necessary, right? So if column 1 dominates column 3, that means that the implicants that cover 3 also cover 1, but not the other way around, right? For example, let's say E and F, right? They do cover 1, but they don't cover 3, right? So this relationship doesn't work the other way. Questions? Okay, so we're going to get rid of this dominating row. A column, dominating column, right? So we get rid of dominated rows and dominating columns, and it's important to understand why we're doing it. So it's not just incantation or anything like that. Okay, let's see if there are other ones like that. Does anybody see other dominating columns?
Yeah. I believe 8 dominates 12.
That's right. So, and keep in mind that everything that is crossed out, imagine that it's not there anymore. But 8 dominates 12 in any case, right? So the 8 is going to be covered by C, D, and E, and 12 is covered by C, all right? But C will cover both 8 and 12, so we don't need the D and E, effectively, right? So we can just cross out this whole column. Oh, I think, did I miss something? 7 dominate, oh yeah.
Doesn't I'm sorry.
Go ahead.
Doesn't 3 also dominate 7?
No, not yet.
Oh,
It doesn't
yeah, sorry.
because of the I.
Yeah, I missed
But
the I.
but the other student is right. So 8 dominates 12, but also, right, 7 dominates 15, right? And it didn't do it before we crossed out row H, but now it does. So in the slide, we're going to get rid of 7 first, right? 7 dominates, even though the student was right about 8 and 12, we'll do that in a minute. But first, 7 is covered by B and by I, and 15 is covered by I, right? But that I, it also covers 7, so we don't need all of the other implicants that cover 7, namely B. We don't need it, so we're going to cross out this dominating column, and now we're going to move on to 8 and 12, right? So 8 dominates 12. Again, 8 is covered by C, D, and E, but we only need one. And the one that also covers 12 is C. So we'll just keep C, and we'll get rid of this column. OK, so the first step we had to skip because there were no essentials. And we did the second step with the red lines and the third step with the blue lines.
Question, Professor.
Yeah.
Wouldn't 4 dominate 12?
I think you're right. Looks like 4 should dominate 12. Let's see if I missed it. Did I? It looks like I may have missed it. Why did I miss? Yeah, it looks like I missed it. But who is this? Is this Jordan again?
Yeah.
Yeah, it looks like Jordan is right because 4 is covered by C and by F. And then 12 at this point is only covered by C. So we should have crossed out 4. But I missed it. And I guess we can try to use it as a teachable moment. If you miss it and you keep going, you will have a chance to sort of catch up. So let's see. I don't remember when I made the slide, but let's see if I redeem myself in the end. So let's look back to 1, right? Find essentials. Do we have any essentials at this point? Meaning, do we have any columns that have just a single X in them?
15. 15.
15 has a single X. Any other ones?
12.
12, yeah. So those two. So what I did here is I just redrew the table. It's the same table as it was before. Oh, here it is. Here it's okay. Here is the state of the table from the previous slide, right? I did miss, 4 and 12.
And Professor,
I'll ask. Yeah.
sorry, does G now dominate B? And does G now dominate D?
Here's the thing. So yes, G dominates B and D, right? However, we have to do these in sequence, right? So we first try to remove essentials. The first time around, there were no essentials. Then we did the dominated rows. We got rid of the row A and H. And then we did the dominating columns, right? And I get rid of 1, 7, 8, and looks like I missed 4. But let's see if it works out in the end anyway. But yes, 4 should have been gotten rid of. Then
So
we go back. Yes.
does C now dominate F?
It is, but we cannot go back to step 2, right? After step 3, we have to go back to step 1. We have to do it, repeat them in this sequence. So I think that the only thing that I missed is for dominating 12, but actually maybe I didn't miss it. I see. So here's the thing. The step 2 and 3 are sort of happening, well, let's say simultaneously after the 1, right? So first you try to remove the essentials, then you remove the dominated rows and dominating columns, then you pause and you look at the new state of the board, and then you try to remove essentials again, right? And now before we do that, I want to clean up this table, right? So this table has a bunch of rows and columns crossed out from it. They are crossed out without actually having anything removed, right? So now that we are done crossing them out based on the state of the table as it was in the beginning, right? Now we're going to redraw the table. And we're going to redraw it exactly as it was, but we're simply going to skip the crossed out rows and columns, right? So because A was crossed out and H was crossed out, we won't have them. We'll just start with B, and then when we get to G, it will be followed by I. So we're literally removing those rows as if we were removing rows from Excel. And whatever X's were in them, they disappear. And the same thing happens to columns. So column 1, 7, and 8 get removed along with all of the X's there. And this is what is left. The table, with 1, 2, 3, 4, 6 rows and 5 columns. Right?
Great question. So if 2 and 3 are happening at the same time, then why is 7 dominating 15 if you were considering H still being there?
Let's see. You're right. They're not happening at the same time, and it does look like I missed 4. However, it may still work out, right? Because everything that we're doing, right, is not changing the logical equivalence of the function, right? So all of these crossings out, we only do them because we're not changing min terms, right? All we're doing here is we're picking and choosing between implicants, right? This is something that with a K-map you would just be doing willy-nilly visually. So the fact that I missed crossing out column 4 here, I didn't spoil anything, right? It's just I may have more steps further on, right? So this, who pointed out that 2 and 3 happen sequentially? Who was the last student who spoke?
Me.
Who? Jordan, yeah. So Jordan is right. So Jordan is correct, but this is not a fatal error, right? If you miss a row or a column, right? As long as the crossings out that you did do, right, did not sort of break anything, right? If you sort of like miss one or whatever, you will have a chance to catch up to it, right? So and we're catching up to it here, sort of, right? So the 2 crossed out rows and the 3 crossed out columns are gone, and this is what we have left. And we're back at step 1, where it says find essentials, put them in minimal form in progress, and eliminate from the table. Right? So again, do we have essentials here?
$12 and $15.
12 and 15, that's right. Yeah, so for 12, the essential implicant is going to be C, and for 15, it's going to be I. C and I, right? So had I crossed out 4, right, I would still have gotten 12, right? I would still have gotten C. Right? So again, as I said, it's not a fatal error. In any case, now that I found C and I wrote them down in my ongoing sort of like minimal form, and now I'm going to eliminate them from the table. And I'm going to eliminate them so thoroughly that I will remove not only columns but rows as well with these implicants, and that will definitely shrink the table a lot.
So when do we know to stop the iterative process?
When there is nothing left to remove. So you'll see that in a second. So look, C intersects 4 and 12. So we're removing C and all of the x's that it intersects. And then we're removing I, and we're removing the column that it intersects as well.
Could you repeat how you determined to remove C and I?
Yeah, so good question. So the question is like, how did I figure to remove C and I, right? So we made the first pass, and this is the first step of the second pass. And we're asking, find essentials in this table and put them into the minimal form as we're building it, right? We know that the essential implicants are the implicants that cover a 1, and no other implicant covers that 1. So the 2 that we identified were 12 and 15. So 12 is covered exclusively by C, and 15 is covered exclusively by I, right? No other implicants cover. So only C covers 12 and only I covers 15, and those are essential. So I'm writing them down into my minimal form, so it's going to be C plus I. And once I wrote them down, right, I can just clean up this table a lot. Well, first of all, I remove them, C and I don't need to have them in the table anymore because I already wrote them down as essential. But then I'm also going to get rid of all of the ones that C and I covered, right? So I only covered 15, so I'll get rid of 15. Now C covered 12, yes, it did. So of course I crossed that out. But it also covered 4, and I crossed this out. Okay? So at this point, the fact that I missed 4 being dominated, 12 being dominated by 4, and I could have removed it then, well, it got removed now, right? So if you're doing this iteratively, and if you miss something, it's okay. But if you remove something mistakenly, then it's not okay. Does that make sense? let's pause here, and I want everybody to see this. Ask me questions about it. Right, so that oversight, right? It's caught at this point, and now we're fine. It's now as if I didn't miss it. No questions. Okay. All right. So now our table is, shrinking. Yeah. So we did this step 1. We removed the C and
Sorry,
I.
Professor, I'm so sorry to interrupt you. Since we got rid of C and I from the table, wouldn't that make 4, like, wouldn't it just leave F for 4?
Well, so look, C, we're removing C, right, because it's essential implicant. It's the only implicant that covers 12. Is that correct?
Yes.
Yes. It happens also that C also covers 4. Is that true?
Yes.
Yes. It also happens that F covers 4 too. How many implicants do we need to cover 4?
Okay, I see. I got it. Yeah.
Just one.
Yeah.
We only need one implicant to cover 4. For that reason, we can just get rid of 4 entirely and don't worry about other implicants covering it as well. Effectively, what I could have done in the previous step, it just happened now.
Right, I see it now. Yeah.
Yeah. Okay, good. Very good. So now imagine that those green columns and rows are not there, and now we can move to step 2. Remove dominated rows. Do we have any dominated rows?
I believe G dominates both B and D.
Yeah, it looks like G dominates both B and D, right? So anything that D covers and anything that B covers, G also covers. And we only need to cover things once, so we can get rid of duplication. So here I redid the table. Right, so this little table is the same as this big one minus all of the green stuff, right? And now we see that clearly that G does in fact dominate D and B. So we get rid of them, okay? And this is what we have left, right? So far we had C and I were essential, and now we have one more essential implicant, which is G, and that's the last one. Right? There's no more. And we just edit it, right? So it's C plus I plus G, right? The sequence doesn't matter. Any questions about what we did here? Okay, and now we convert them to terms, to literals. Right, complement Z complement T plus X complement X complement Y plus YZT. Right, so we can go back to our table and just recall what they represent, right? So C, C, G, and I, right? So C and I cover 2 ones, and G covers, I think, and I'm sorry, I covers a single one. Any questions about this? Right. In the end, we achieved the same result that we were able to achieve just with the K-map, right? But you need to know both methods. So this method doesn't have the visual aspect of actually looking at the K-map. You're just following steps. As you saw, it's kind of forgiving. if you miss something. However, if you remove something mistakenly, then it will be wrong. Okay, if there are no questions, I'm going to go on to the next topic that is actually more fun than this.
Is there a benefit to using this over KMap?
Well, the benefit is that you can teach a computer to do this more easily, right? You know, you don't, you're just following steps. Like you're literally following these steps in a loop. So it's very easy to turn this into a computer program. Whereas, you know, obviously you can write a program that would teach, you know, a computer to analyze a K-map, you know, but this is sort of like a more direct algorithmically than using the K-map. Okay, again, we got the same answer that we got one with K-map. This is the second part of the homework that I posted yesterday, but it's due tomorrow, and it's just an exercise. Perhaps, though I don't require you to do it one way or the other, you may choose to do this using the tabulation method. In fact, why don't we do this? For 17.2, let's do this using tabulation method. Right? Because there will be one question like this on the final exam, so you want to practice at least a little bit.
Oh, I already did it, but I used the axioms and like properties of
That's fine. That's fine. You get credit for the homework, but I just recommend that at some point before the final exam, you want to practice this, okay?
Okay.
Yeah, it's just a recommendation. It's a recommendation. Okay, new topic, right? So now we're going to look at actual circuits. We're going to look at two different types of circuits. One is called a half adder. The other one is called a full adder. We're going to start with half adder because it's simpler, right? And in fact, full adders are made out of half adders. Okay, what am I talking about, right? Well, I'm talking about mechanism for adding numbers, or specifically adding binary numbers. So to remind ourselves how to do that, we did that earlier, but let's remind ourselves, we're going to add two binary numbers and figure out what are the actual steps involved, right? So here we have two binary numbers. One is 13, I'm sorry, 11, one is 11, and the other one is 5, right? So we have 11 and 5. So let's add them, right? So 1 plus 1 is 10. I'm sorry, so 11 and 5, that's decimal, but let's stick with binary, right? With binary, 1 plus 1 is 10, which is 0, and 1 carries over. Then here we have 1 plus 0 is 1, plus that carry is 10, so it's 0, 1 carries over. 0 plus 1 is 1, plus carry is 10, so it's 0, 1 carries over. 0 plus 1 is 1, plus carry it's 10, 0, and 1 carries over, and it drops down. So the result is 10,000, or in decimal, that would be 16. Okay. Any questions? So we know this. Okay. So now let's look at each steps in this long addition. For example, in this one step, we have two inputs, an output, and the carry, right? So here we're adding only two numbers, and if we don't care about carry, we have two inputs and one output. But once that carry was passed along, to make all of the subsequent additions, right, it was a little bit trickier because we had three inputs. We had, A, B, and carry. Okay. Does everybody see the difference between this first one from the right and then the remaining ones that received the carry? Right. So if we think of each of these little additions as functions, this one in the beginning only has two inputs. whereas the rest of them have 3 inputs. Right? We can say that, let's say, it's A, B, right? So all of them have the A and B input, but the 3 on the left have also the carry. Yeah? So we call the red one a half adder, where you add 2 things, 2 bits. And we call the green one the full adder. It can add 2 bits and can receive a carry also. Okay, so now we're going to build them. In this representation, right, this is a black box half adder, right? So we don't know how it works, but this is the box. And half adder has, as we just determined, 2 inputs, A and B. But it also, interestingly, has 2 outputs. We haven't seen that. All of our functions, have a single output, and you really cannot have function with 2 outputs. So what you should think of it as 2 separate functions, right? It's 2 parallel functions that share the inputs, right? But then produce, 1 output each. So this half adder produces the sum, which in this case is 0, right? And it also produces a carry out, which is that one. Any questions about this? No questions. Very good.
Wait, I have a question. So the sum, the S, it only outputs the first digit of the sum?
Yes, that is correct, right? Because these are single bit adders, right? So with any single bit adder, your sum, your result is a single bit, right? But of course, we don't want to lose the whole, magnitude of value, right? And that is the carry out, right? So the sum is considered 0, 1 plus 1, but also there is a C out, and that one is 1. Does that make sense?
Yeah, thank you.
Yeah, so, or another way to think about it is that with all of our Boolean functions, right, if you imagine them as electricity, no matter how many inputs we have, and each input can be either on or off, in the end, the output is Boolean. It's either on or off, either true or false, either 1 or 0, right? So same thing, this S is a function, and we can even imagine how it works inside, right? If both are 0, it will be 0. If either one of them is 1 and the other one is 0, it's going to be 1. And if both of them are 1, it's going to be 0, right? So this S function, what does that remind you of? It's we've seen it. It's a what?
The majority function?
It's not a majority function, right? Because with the majority function, 1 and 1 would make 1. I heard another raised hand. Any other thoughts?
Is it the OR function?
You're very close. You're almost there.
Is it the NOR function?
Is it the NOR function? You're very close, but still, it's not OR, it's not NOR. What's the other one? What?
XOR, that thing?
Yeah, it's the XOR, right? It's the exclusive OR. It's going to be 1 if only one of them is 1, but it's going to be 0 if either both are 0 or neither are 0, right? So S, you could make it with a single XOR gate. Of course, you remember that the XOR gate inside has other gates. Anyway, so that's the sum. That's all it does. But then we have the secondary function, the cout function, right? That is also affected by A and B, right? Separate function. And that one will only be 1 in what condition? So out of the 4 possible combinations of A and B, right, could be 0, 0, 0, 1, 1, 0, 1, 1, right? what is the only combination under which C is going to be 1?
If there's
1, 1.
0.
So I think I heard Chelsea. Who was this?
Stephanie?
Stephanie said 1, 1, right? That is correct. So only when both A and B are 1, there will be a carry 1. Right? If they're both 0, if only one of them is 1, or only the other one of them is 1, carry is going to be 0. So if we determine that S could be made with a single XOR gate, how could we very easily make C or carry out?
Oh, with and?
Yeah, just like an AND gate. Yeah, so something like that. Yeah, there are many ways to do these things, but that would be super, sort of like straightforward. Okay, so that just puts it in perspective. But this is our half adder. This is it. It has 2 inputs and sort of 2 functions that produce 2 outputs based on both of these inputs.
Sorry, C out is the carry, right?
That's right, carry out. So the actual one itself, those little red ones, we call them carry, right?
I was reading it as print for some reason.
If this is not C++, oops. And we call it in this case carry out because it comes out of the half adder. Because as far as the full adder is concerned, this carry out will become carry in. And of course, full adder will also have carry out. Yeah, so let's see that step by step. So just one last thing to say here. We're going to refer to half adders as HA. Okay, so we know everything about the half adder. Now we're going to look at a full adder, or FA, right? So FA still has the A and B input, the 2 bits from the 2 numbers being added, but also it needs to receive this carry out that came out of the half adder, or from a previous full adder, right? Because we have a full adder after a half adder, and then we have another full adder and another full adder. So full adder has to receive A and B, and it can also receive, or will also receive, does receive a carry in that can come from either another full adder or from a half adder. Right? And there's still 2 functions here, 2 outputs, the sum and the cout. So cout just stands for carry out, right? So the implementations of these functions are going to be a little bit trickier because there are 3 inputs. We don't need to go into them like just the second. We'll look at them in a minute. But because you know how you could implement a half adder, you can believe that implementing full adder is also possible. But for now, just for the second, we can think of it as a black box that has 3 inputs and 2 outputs. Any questions about that? Okay, very good. Okay, so what we just said just verbally, now let's look at it in a little truth table, right? For the half adder, we have the 4 possible combination of inputs, and we have the 2 functions, the sum function and the carry out function. And we see that the sum behaves very, very much like a XOR, and the cout behaves very much like an AND. Okay, but we want to make a Boolean function, right? We want to express it as a Boolean function, and to express S as a Boolean function, the ones are going to be in these 2 rows. So in this row, it's complement of A, B, and the second one is A complement B, right? So that's what we have. This is the expression of S as a Boolean function, complement A, B, or A complement B, and for the cout, there is only one minterm, only one, and that is AB. So AB, and then we can unwrap them or multiply them out. Actually, no, this is not. This is the fourth axiom, right? We convert them, right, into. We take the sum of products and we convert it to products of sum. Product of sums, and the product of sums is complement of A or B and A or B. And that's for the sum. And for the cout, we do De Morgan's, right? We convert a product into a sum of complements, and then we have to complement the whole thing. So these two parts of these functions are the same. So we'll be able to reuse them, as it were, when we're building a circuit. So here we have it. Right, rather than having two completely separate circuits, which we could have done, here we're having a circuit that is, well, let's say more integrated, right? Where we have both A and B are negated. Well, actually, let's see. They're negated going down. Then they go into an OR, where here they go into an OR without negation, and they go into an AND that produces sum, and here it's reversed and it produces C, right? So this is a half adder with 3 gates. We're not counting inverters, right? We have 2 OR gates and 1 AND gate, right? So we achieve implementation of both of these functions together with only 3 gates. So this is obviously not the only possible implementation of half adder, but it's probably one of the simplest ones in terms of number of gates. Any questions about that? Okay. So the next assignment, right? Express this half adder using only NOR gates, right? NOR is the not OR, not XOR, NOR, right? And you can use also as many of the inverters as you want. Okay, any questions about this homework? So this is something that you will just draw on paper and take a picture of. Okay. All right, let's proceed. Okay. Full adder. So this is going to be a little bit clearer. This is the truth table for full adder. It has 8 rows, right? Because we now have 3 inputs, A, B, and carry in. Right? Still have 2 outcomes, 2 outputs rather. We have the sum and we have the carry out. Yeah. Now let's quickly look at the behavior of the sum, right? If they're all 0, it's 0. If just one of them is 1, it's 1. If 2 of them are 1, it's 0. One of them is 1, is 1. Right? So basically, there are sort of 3 groups. We can group them into 3 possibilities. When all 3 are 0 or are 1, it's 1. When all are 0, it's 0. When 2 of them are 1, it's 0. But if it's one of them is 1, it's 1, right? So can you express it more succinctly? Can somebody express it in terms of how does number of ones determine the outcome of the sum function? Right? With the 3 inputs, we can have 0, 1, 2, or 3 ones. Yes, everybody sees that? So how does the number of ones among the inputs predictably affect the sum function, the outcome of the sum function? Right? There are 8 possible combinations of inputs, of the 3 inputs, right? But they can be grouped into 4 groups, right? We can group them by the number of ones in the 3 inputs, right? The total number of ones. Is everyone, are you still there? Can you hear me?
Yes.
Hello? Yes.
Yes.
Okay. So, am I not clear about what I'm asking? Okay, let me phrase it differently. Can you predict the outcome of the S sum function by simply knowing how many ones you have here, right?
If there's 1 or 3 ones, then the S function is a 1.
Okay, correct. And what else? 1 or 3, it's
If there's an
true.
odd number of ones.
Was that?
If there's an odd number of ones.
That's it. Yes, thank you. That's what I was looking for.
Hamming distance here.
Yeah, you can express it through Hamming distance, but well, actually, Hamming distance requires 2 strings. Here, we can look at just 1 string, right? When we look at any one of them, if there's an odd number of ones, the sum is 1. If there is an even number of ones, including 0, it's an even number, then the sum is going to be 0. Okay. Anyway, so that's the behavior of the sum function. And the carry out function, let's see. It's 0 when you have 0 ones, 1 1. When you have 2 ones, it's 1. When you have 1 1, it's 0. When you have 2 ones, it's 1. So anybody can make an observation, like a similar sort of like simple observation that will predict the outcome of the carry out.
If there's an even number of ones for carry out, then it'll be 1 for carry out.
Even.
Oh,
right?
no, I'm wrong.
No,
It's,
not
yeah,
even.
it's only
Yeah,
for
okay.
if there's 2 or 3 ones.
Right. So let's try a different one.
It's like a majority circuit?
That's right. It's like a majority circuit. Was that Patrick?
No, it's nephew.
Nephew. Okay. Very good. That is right. And so when all of them are 1, it's 1. When 2 of them are 1 is 1. So it's this one, this one, this one. Yeah. But if it's 1, only one of them is 1, or if 0 of them is 1, it's 0. So this is like a majority circuit. Right, so just in your mind, you know, kind of like, but you say, oh, it's just a majority circuit. But remember that the majority circuit was complicated to build, right? So when we're building this full adder, we're not going to make it out of the majority circuit, but we could. Right? Okay, we're going to make it out of something as simple as we can. So when we look at the sum, we have complement of A, complement of B, and C. Then we have complement of A, B, complement of C. The next one is going to be A, complement of B, and complement of C. And the next one is going to be all true values, A, B, C. Okay, so these are the min terms of the sum. Now for C out, we'll have 4 minterms also. It's complement of ABC, A complement of BC, AB complement of C, and ABC. So let's put them on the K-map. So this is the S. Does anybody see any prime implicants here? Any large prime implicants? Tricky, right? Okay. The answer is no, right? So you, your minimal form, you need all of your min terms with all of the literals. Okay, so that's our sum. Okay. Now let's do C out, carry out. This one's a little. We can work with this one. Yeah. So we have 3 prime implicants. Though, are all of them essential? Real quick. No? Which one is not essential?
They're all essential.
They're all essential. Thank you. So that means that it will have, the minimal form will have 3. It will be sum of 3 products. Yeah? Which doesn't seem that simplified, but it is a little simpler than sum, even though they started the same. Yeah? So we were able to simplify the C out, but not the sum. Okay. Yeah, as you have noticed, this is the majority function. Very good. Now, construct a full adder, that's the next assignment, using only half adders and one other gate. Yeah. So as I said, you can certainly make it out of a majority function, and in some cases people do. But for the homework, I would like you to, after you did the previous assignment, which was to make a half adder, then you can pretend that that half adder is just a single thing, like an integrated circuit. Like, I don't know, make it a circle or something, and then you can draw the full adder circuit using as many as you want of those half adders connected by either and or. Okay, any questions about this assignment? Right, so all of these are drawing assignments. No questions. I noticed that today, I think I'm a little bit low energy because I'm doing 3 lectures a day starting from yesterday, and it's only the 2nd day, and I'm already getting a little tired. But are you guys low energy because of the heat wave?
Yes,
What's
definitely.
Yeah.
92 degrees.
Yeah, no, I get that. Well, I hope that, I think the material right now is interesting. It's fun because we're building the actual things. Why don't, are there any questions about any of this? It wasn't that much of the new stuff, but it's, we're just doing it incrementally.
In in-person class, do you actually build the circuit?
No, when I say when I say build, you draw. However, right? I think there is at least one course taught by Eric Schweitzer. I forget. I should look it up. What it's called, where you actually do build circuits. It is a course that is offered every other. It is a course that is offered at least every other semester, and it is a major elective, and I highly recommend it. Has anybody had Professor Schweitzer in any course before?
Yeah, for 150.
For 150, okay. So he's a wonderful professor. He's great. He's a funny person, but also just like really witty. But also try to take his hardware course, right? it's really rewarding. Now, because it's actually became more popular, they may offer it every semester now, but definitely once a year. Okay, so if there are no other questions, I'm going to let you go a little bit early today, but I need to talk to at least one person in the office hours. So what I'm going to do now is I'm going to sign out, and then I'm going to start another session called Office Hours Now, and I will talk to that student there. Okay, so I'll stop recording.
Thank you, Professor.
Okay, thank you. I'll see everybody tomorrow. Do the homework.